Okay, it's a pleasure for me to announce the next speaker of this afternoon session, which is David Gaiotto. He will talk about giant gravitons in twisted holography. Please go ahead.
Hello. So I'm going to discuss a recent project I've completed in collaboration with my student Kasia Vuzik. It's the main subject of this project are correlation functions of determinant operators in unequal force superior mills. So these determinant operators are operators which, inserted in the quantum field theory, impose the existence of a D-brane and holographic dual which reaches the boundary in a specific way. In particular, the operators I'm interested in are of this sort. You take a complex linear combination of the 6 scalar fields of unequal force superior mills. You add a multiple of the identity, and you take the determinant. And you require the coefficients of this complex linear combination to be a null vector in C6. And then this holographic dual description of this operator is known, or conjectural at least. It represents the insertion of a giant graviton D-brane, meaning a D-brane which asymptotically near the boundary wraps an S3 inside S5 and approaches, from the point of view of ADS5, it looks like a line reaching the boundary. And that's why it's described by a local operator there. The choice of complex vector N determines essentially the orientation of the S3 inside S5. So the real imaginary part of N are like 2 vectors in R6. And so they give you a direction where you could cut an S3 out of an S5. And this parameter M controls roughly the size of this S3, meaning that when M is 0, it's a maximal S3, which is like an equator of S5. But as you increase M, the S3 becomes smaller and smaller and moves towards the poles. And the objective is to study a correlation function of many determinant operators in the quantum field theory, possibly decorated by some traces. And as the title suggests, I will ultimately specialize to a configuration which can be discussed within the context of twisted holography, which is sort of a protected subsector of the full holographic correspondence, where calculations can be done with free fields, essentially, where the interactions can be turned off, but all the complexity of the large N expansion remain. So, according to holographic prescription, the result, in order to compute holographically correlation functions for a collection of determinants, here I place 4 at the boundary, we need to look for semi-classical saddles for the D-brane. So the dominant saddles have just ADS5 times S5 geometry, but because the operators
Sorry, David, can you hear me?
Yes.
The sound.
Sorry? I'm sorry, there seems to be some problem with internet connection. Let me hotspot it.
Yeah, Davide, we just had some connection problems, so we lost
Yes.
seconds. So if you can,
I'll try to move to
and resume, that would be great. Thanks.
Okay, is it better? Hello?
Now we could hear you, yes, but just like 5 seconds ago, we're still frozen and no audio. But just try, and then we'll take it where it is.
Okay, so. Okay, I hope this will work. Okay, so in order to evaluate in large n limit holographically the correlation function of several of these determinant operators, you need to consider a D-brane which wraps some from manifold which approaches the boundary in a specific way determined by the choice of parameters m and n at each of the points. Then once you find this classical solution, the saddle will contribute with an amount that is proportional to e to the minus n times the action of this D-brane times the perturbatory expansion of that should be string theory in the presence of the D-brane. It's once find the saddle is allows to write correlation functions because you can also insert closed string operators, which are string mode, closed string modes, and you will have diagrams in the bulks, like, for example, a bulk to boundary propagator from the D-brane to the boundary.
Interrupt you one
Yes.
I think there might be a bandwidth problem. So even though it's non-ideal, could you turn off your camera? Maybe that will be better.
Okay. I think my camera is already off.
Now it is. Nicholas did it. Yeah. Sorry for these problems, but we'll try to not interrupt you anymore. So just go ahead.
No problem. I mean, I switched to internet connection. Okay, so in general, given the boundary conditions of the D-brane endpoints, there might be multiple possible configurations with the D-brane which contribute to given function, different type of connectivity. Or not, on and so forth. There, in principle, I can look for solutions with various connectivity, and even once the connectivity is specified, in principle, there could be multiple solutions. And I imagine, there will be Stokes phenomena where different saddles might exchange dominance depending on the values of the parameters. But today, I'm not going to concern myself with the competition between saddles at all. My objective is to understand the saddles, individual saddles. Now, this operation at large n at strong large tooth coupling is very challenging. So instead, I'm going to focus in a sector where the coupling can be ignored, and where the saddle point analysis is still actually non-trivial. So the sectors is the Chiral algebra subsector that was introduced by Beam, Lemos, Liendo, Pelaers, Castelli, and Van Ries some time ago. This subsector essentially consists of correlation functions to the scalar fields of very specific linear combinations of the scalar fields, which depend on the position. So to get to this subsector, you impose two restrictions. First of all, you require all operators to lie on a plane. Here parameterized by complex coordinate z, and then you you pick 4 of the scalar fields and you take these position dependent combinations of this for scalar fields, where you pick a very specific anti-holomorphic dependence on the anti-holomorphic coordinate. This choice allows you to essentially it's such that correlation functions become holomorphic. So these linear combinations essentially behave like two-dimensional Chiral operators to a specific beta gamma system, valued in the joint of UN. And then the effect of the gauge interactions is simply to restrict you to operators which are in the cohomologies of a certain BRST supercharge, which is the standard supercharge you use when you gauge some symmetry in a chiral theory. So the requirement that the operators are BRST closed gives some nonlinear constraints, in a sense, contains a bit of the interactions, but once you know the operators, the calculations do not have any interactions. The calculations are just done in free field theory. And so matching this calculation to some geometric gives a nice example of a situation where large N combinatorics can produce geometry directly without having to turn on the Tuft coupling. So in this particular example, it turns out that the determinant operators built out of these linear combinations are actually in the homology, so they can be used directly in the Chiral algebra. They are part of the Chiral algebra subsector. And so our objective is sort of a subsector. What is up in the some time ago with the context of twisted holography. So our claim is that this Chiral algebra for phosphor mills is holographically dual to the B model, the topological B model on SL2C. And also, you can argue in the same way that the three branes in the S5 in the Chiral subsector should map to the D-branes in the Hello? I'm sorry,
Hi, Davide. We
Yeah.
hear you, but it's really difficult. Yeah, your connection is probably not good enough. Do you have another option, or is it the only?
Well, I switched back to my house Wi-Fi. I mean, I tried both the house Wi-Fi and the hotspotting from the phone, and I have no idea what's the likelihood that both fail at the same time.
Well, the problem might be the Wi-Fi.
At the moment, I'm on the Wi-Fi again, so I switched out of the phone. How is the quality? Still bad?
I mean, there are various things you can do. You can set up a lower screen resolution, and you can limit the frame rate to something like 2 or 4 frames per second. This is in the video options.
Well, at this point, okay.
Sharing options, does that help? No, it does not. somewhere there.
I mean, let me see what happens. So if I mean, at the moment I don't have no video, right? I'm just sharing slides. Can you hear me?
Yeah, yes, we can hear you. And just now discussing about the connection problems, the connection was good, but yeah, it's just not good, I think, in general. You could send a PDF of your file, maybe we can show it locally, and then you don't share anything to limit bandwidth. But what's
I think it will cost, I mean, there are like, let's try a little bit longer like this.
Yes, yes, please do.
Okay. So, right, so in this twisted holography dictionary, the D-branes in the D5 times S5 would reduce to D-branes in the B model, which wrap an holomorphic curve. So, so this sort of pictures in the twisted holography setup should represent holomorphic curves inside the Calabi out, which is SL2C. SL2C topologically is essentially ADS3 times S3. And intuitively, this is an ADS3 times S3 submanifold inside this ADS5 times S5. But I have to confess that we have not worked out the details of how but we've not done the extra step of converting those holomorphic curves into four manifolds in a DS5 times S5. Anyway, part of the reason we looked at this was a beautiful work by Young, Komatsu, and Vescovi. In this work, they studied the classical saddles of the correlation functions of determinants, the Lagrangian saddles of the correlation functions of determinant operators for a free n equals 4 superior Mills theory. This was what I found fascinating, is that the existence of multiple saddles and their connectivity properties were already manifest in the free gauge theory. It's not quite obvious, it's not obvious at all how these saddles would evolve though when you turn on the coupling. So we thought of looking at the twisted holography setup precisely because we don't have to turn on the coupling. We can just borrow the results directly for the free theory. So the strategy to compute these saddles is straightforward, although it has several steps, and I'm not going to review them in details. But schematically, the first step is to fermionize all the determinant operators. You write the determinant of a matrix as a Grassmann integral with some auxiliary fermionic variables in the fundamental and anti-fundamental representations of the gauge group. This is, by the way, a pretty natural way to understand why determinants represent giant gravitons. The moment you fermionize them, your path integral looks like a 't Hooft expansion with both matrices and vectors. And so you get the 't Hooft combinatorics give you Riemann surfaces with boundary. But I should caution you that if you just do the naive perturbative expansion using this sort of action, you will always land on this kind of saddle where all the D-branes are disconnected. And a slightly more complicated analysis is required to understand the perturbative expansion around connected saddles. Anyway, the remaining step of the calculation involves integrating away the 4D scalars, which gives you a quartic action for the fermions, and then a Haber-Stratonovich transformation, which rewrites the quartic action as a Gaussian action with some auxiliary degrees of freedom which have been integrated in, which are essentially a K by K matrix, where K is the number of determinant operators. And so the final result is just a final dimensional integral involving this k by k matrix with some action. Some action which has a sort of a tree-level and one loop part, which are all of order n. And so both contribute. And you can then look for saddles to this classical action, or this semi-classical action for this matrix rho. The saddle equations simplify a little bit in the Chiral algebra limit. And in particular, they look like actual matrix equations, which is not the case for general orientation of determinants. And they take a very interesting form. So let me denote as zeta a diagonal matrix whose entries are the positions of the determinant operators at the boundary. And let me denote as mu a diagonal matrix whose entries are the orientations of the determinants, the specific linear combination between of the two scalar fields. And let me set the diagonal components of this metric rho to be the m parameters. And then the remaining of diagonal components are constrained by this equation that says the commutator between zeta and rho plus the commutator between mu and rho inverse should be 0. After you find a solution of these equations, you can reconstruct the action in various ways. For example, by using the fact that the diagonal components of rho inverse are the derivatives of the action with respect to the masses, with respect to these m's. A nice feature of these equations, which is immediately visible, is that I can look for solutions which are block diagonal, where rho has several, is 0 outside some block diagonal parts. Then the equations sort of hold within each block. And this represents solutions with multiple connected components. If you want to look for a solution that represents a what do I do with these equations? Our objective, to remind you, is to identify an holomorphic curve in SH2C, which might represent holographically these saddles. Now, whenever I see equations which involve commutators, I think of integrability and I think of Lax matrices. So what we did was to build some commuting matrices, some matrices which depend on a spectral parameter A, and which commute whenever these equations hold. Now, if you want to know an equation which has a sum of two commutators, should remind you of something like a Hitchin system. Anyway, the matrices are elementary to write down. You take linear combinations of these diagonal matrices mu and zeta, and of rho and rho inverse. They are linear in this parameter A. I can define two matrices B and C, and then three matrices B, C, and D. They all commute, and they satisfy a matrix equation. AD minus BC is equal to 1. Why is this nice? Well, now I can look for simultaneous eigenvalues of this format of these three matrices. Let me call these eigenvalues b, little c, little d. So for every value of A, I'll get roughly k values for B, C, and D, which satisfy also AD minus BC equal to 1. So this gives me an holomorphic curve inside SH2C. Could this be the D-brane we're looking for? So we did several tests. First of all, at large A, it has the correct asymptotic shape to represent the insertions of determinants. It's actually quite easy to study the large A. Here we need to study the behavior of this curve as you approach the boundary of SH2C, as you go to infinity in SH2C, which means at large A. And at large A, these matrices essentially become diagonal. And so you find k branches along which the ratio of B and A and the ratio of C and A are fixed. And this turns out to be precisely the giant graviton shape that we're looking for. the second test we did was to do a calculation like this. So we inserted, within the Chiral algebra, we inserted some single trace operator representing a closed string. Is supported in a codimension one, complex codimension one locus. So this integral of the curve just becomes finding the intersection between the propagator and the curve. Still, is rather non-trivial calculation. A lot of moving parts that to align properly to give a match. So this really, this really verifies that a bimodal calculation reproduces the large N behavior of the correlation function. We also did some checks involving the global symmetry algebra. In the work with Kevin, one of the main ingredients we employed to match Chiral algebra correlation functions and the bimodal setup was to observe that both sides had a symmetry algebra at large N, which looked like holomorphic diffeomorphisms of SL2C, essentially holomorphic vector fields, globally defined holomorphic vector fields in SL2C. And so what we could do here was to check that acting on both sides with these holomorphic vector fields would give matching effects. So that sort of, it would deform the shape of the spectral curve just in the same way as the holomorphic vector field should. And finally, we did a one loop check in the sense that we looked at situations where you move where you adjust your parameters so that two of the branches of the D-brane touch inside SL2C. And the one loop, so that the one loop correction in the bimodal diverges in that limit, and we find the corresponding divergence in the matrix model in the Chiral algebra calculations. Okay, let me see how much time will I have. So what time am I supposed to stop? Am I already behind, or we have a few more minutes?
We talk for about 35 minutes, so there's 10 minutes for discussion. And
okay, so I still have 8 minutes. Okay.
We lost some time, so try to see where you can get in 6 minutes.
Yes. So no, it's okay. I just have. So this is what we did, and this is what we would like to see done in the future. So one of the basic questions I would like to understand is which saddles, do actually contribute to a calculation in holography. So here, here I said, given an M4 and it is 5 times S5, we expect to be able to find a holomorphic curve in SL2C, which represents it. So there are sort of two questions one might ask. First, does every M4 represent a saddle in the equal 4 super Mills? Probably, but we don't know for sure until we check. And then, does every M4, every holomorphic curve represent some M4? So in order to answer these sort of questions, it would be nice if we could demonstrate that every holomorphic curve in SL2C with the correct boundary conditions is actually a spectral curve. We didn't manage to do that for a generic curve, but we checked it for genus 0 curves. So we checked it for every genus 0 holomorphic curve in SL2C. You can find a row. Obviously, it would be nice to also check subleading corrections. So we essentially did a disk calculation for now. It would be nice to check that the bimodal really systematically reproduces the free field theory correlation functions in the Chiral algebra subsector. I think this is doable. I don't know if it should be done by physicists or by mathematicians, but it's fun that this can be done by mathematicians in the sense that both sides are perfectly well defined. mathematicians do understand very well free field theory correlation functions, and they do understand the B model. As I mentioned multiple times in talk, it would be nice to figure out that part of the twisted holography dictionary which tells you which four-dimensional D-brane shape corresponds to a given holomorphic curve. And this requires a little bit of work by people who's familiar with supergravity, and finding nice D-branes, nice calibrated cycles for D-branes to wrap, which preserve a given amount of supersymmetry. I've been looking in the literature a little bit, but and there is a lot of work on using all complex geometry to find nice supersymmetric D-branes. For example, by Mikhailov. Mikhailov had some beautiful papers on finding complicated giant gravitons using complex geometry. But somehow that doesn't seem to be using the correct supersymmetry. So there's a little bit of work needed to do here to understand the localization of supergravity and of D-branes with respect to the supercharge which is used in the Chiral algebra subsector, which, as I remind you, is a certain linear combination of a supersymmetry charge and a superconformal charge in the quantum field theory. Finally, what I think would be, well, there is a point I forgot to write, sorry. So almost finally, I think these Chiral algebra calculations can provide a starting point for more general calculations, more physical calculations, in the sense that as the coupling does not matter in the Chiral algebra subsector, I can imagine now taking these determinants and rotating them a little bit away from the Chiral algebra subsector, adding a small amount of some of the other scalar fields. I imagine that the correlation functions then would emit some kind of expansion, where the expansion parameter is the product between the two coupling and the perturbation away from the Chiral algebra limit. If this is the case, it might be possible to build up a sort of a near Chiral algebra expansion, where the product of the tooth coupling and the deformations is small, even to the tooth coupling is large. So this has been done before quite successfully for a lot of protected sectors of the theory, and I think it should be done for the Chiral algebra subsector too. And then in that situation, for example, these holomorphic curve saddles could be a good starting point to build the full saddles. And finally, we know the saddle equations for free and equal force super mills, even outside of the Chiral algebra subsector. It would be very interesting if we could manipulate these saddle equations in such a way as to give insight to what the holographic dual of free Yang-Mills theory is. So there has been a lot of work in trying to propose, even recently by Davide and Gopakumar and others, to propose potential holographic duals for free Yang-Mills theory, and to reconstruct a string theory from the Feynman diagrams of the field or the free gauge theory. And I think using giant gravitons as probes could be a very effective way to probe these proposals or to develop them further. And I am done with the presentation.
Okay, thank you very much for this nice seminar. Is there any question in the audience? I see. Okay, Julian, you please go ahead.
This might be a slightly strange question, but so you're looking at these determinants of operators that are basically n by n matrices, and then they are giant gravitons. Do you know, or can you speculate on whether there is a similar story to be told for matrices that are rather of size exponential in n, so e to the n times e to the n, and what would the objects be?
the best I've done at the moment is to understand situations where the matrices are sized as n squared, meaning that one thing you can try to do is to consider large powers of a determinant, say determinant to the power of n. This gives you configurations where you have a lot of giant gravitons which are back reacting in the geometry. And I find that fascinating because it might give you a situation where you can really see a sum over geometries, you know, e to the minus n squared times a closed string action.
Exactly why I'm asking, and also in connection, I think your paper with Rastelli, you know, on this the case in you know, 1D, 2D open closed duality. So there it seems to be like more like e to the n matrices. And so if you can understand those in n equals to 4, that would be very interesting.
Yeah, so something I've done and not published yet is to study the situation where one of the determinants is raised to the power of n. Then in that situation, we know the back-reacted geometry, and we can actually verify that the chiral algebra correlation functions have saddles which are controlled by holomorphic curves in the back-reacted geometry.
What is that geometry?
It's essentially the Coulomb-Brand geometry. It's kind of funny. If you take the geometry sourced by two stacks of the D-branes and you look at it from the point of view of one of the two stacks, the deformation of the geometry is precisely what you would find by a stack of these smoothly closed giant gravitons. We would love to understand a situation where more determinants are raised to a high power. I think at least a situation where two determinants are raised to the power of n should be understandable because the back-reacted geometry is LLM, essentially. More than having 3 or more determinants raised to the power of n would be even more interesting because then, you know, I expect to see complicated Calabi-Yau geometries instead of SHOC. But the gauge theory analysis becomes increasingly complicated. Essentially, you get a multi-matrix model, and I don't see at the moment a chance to do anything analytic there. Although I hear that there are numerical tools that have been developed to do multi-matrix models. So maybe that at some point can be used.
Thanks. That's
but yes.
Okay, are there any other questions in the audience? No, is there any question from the Zoom? Well, if not, then I suggest, yeah, we are sorry for the technical complications, but this can happen in a hybrid conference. But sorry for that, but we enjoyed a lot your talk, and let's thank Dave once more for this nice seminar.